So I'm going to start the recording. So what we're going to do, we're going to kind of push a little bit this week. Basically looking at 3 sections a day. And the reason I'm doing that, we've got spring break the week after. So I'm going to pull up the schedule here real quick. And let's take a look. See what's coming up. Take a look at some of the due dates here. Okay. So you got 3.3 and 3.4 due today. Let's see. Now we're doing 3.6 today. 3.6 is going to be due on Thursday. I might give you some more time to work on some of these over the break. But the goal is really to try to get through, have chapter 3 wrapped up more or less by the time we come back. So that just leaves us chapters 4, 5, and 6. So that being the case, it's gonna seem like a little bit of a push here, but bear with me. If I'm going too fast, let me know. And I can always put together some supplementary videos that could help explain some ideas. So what we're looking at here, we're going to start to get into some more, in a sense, applications of the derivative. And we're going to start out with something called the chain rule. In the chain rule, we're looking at the derivative of a special form. So we've seen product rules, we've seen quotient rules. But now we're going to try to figure out, how do you take the derivative of a composition? So again, we've seen the derivative of quotients, the derivative of sums and differences, the derivatives of products. So how do we deal with this? Well, just to kind of give some kind of idea of what this is. So let's say you have the number line, another number line. We're going to have this. Now bear with me, let me fill in some details here. X will become u by using the function g of x. And then we're going to take u, we'll put that into f. And that's going to give us a point y. Let me draw this a little differently here. There we go. So in essence, what we're doing is that y equals f of u going to be f of g of x. And so this is the idea of composition. We're going to take some number, say on the number line. We'll put it into a function g, and that's going to give us an output u. U is g of x. Then we're going to take u, we'll put into a function f, and that's going to give us an output y. Y equals f of u. So basically what y f of u, well, that's just f of g of x. So how are we going to do this? Well, let me give you an idea, kind of just an example that kind of gives sort of some motivation for what's going to happen. So let's say we have this. Now I'm going to be following along in the text. I'm on page 153. But we're going to start with kind of a simple example, relatively simple. Let's rewrite this as 1/2 times 3x. Now, what we're going to do is we'll let u be g of x, or 3x. So this means that y, the f of u, which will be 1/2 u. Now, what we're going to try to figure out is dy dx. So what we've done is we've taken, again, x, became a u, became a y. So x will go in here, it'll become a u. Then we're going to take this u, we'll convert it into a y. So to come up with the derivative, dy dx, well, we already have y defined as this. Granted, we've taken it apart, but we know it's going to be equal to 3/2. So what we're going to do is rewrite this as 1/2 times 3. So now let's go back to our pieces. We said y is 1/2 u, and then u was 3x. So dy du is equal to 1/2, and du dx is equal to 3. So what this is going to say is this: dy dx, which we found is 3/2 because we know what y was. It was 3/2 x. We can call this 1/2 times 3, or dy du du dx. And you might sort of notice something here. If we were to treat this as fractions, the du's would cancel, and you would get dy over dx. So this is what we're going to get. This is going to be our chain rule. So any questions so far? All right. So if f of u is differentiable at u, and of course u is going to be g of x, and g of x is differentiable at x, then f compositions g of x, which is f of g of x, is going to imply that df dx is going to be df du times dg dx. So any questions about this? And this is a slightly, again, we're saying that u is equal to g, and I'll put it in a more familiar notation. And again, if y equals f of u, and u equals g of x, we can write it just how we saw it a little while ago. dy dx will be dy du dx. Now, the chain rule, if you're dealing in a lot of physics equations in physics, you're going to be relying on the chain rule. It's one of these very, very important things that comes up, and its applications are I can't really speak of it enough, actually. So let me do some examples, and you can summarize this in another way. There's a helpful way you can do this, and they call it the outside-inside rule. And it basically says this: for y equals f of u or f of g of x, for u equals g of x, what you basically get is you're going to take the derivative of f. And we'll start out with our dy du dx. And then you can call this df du dx. Or we can call this f prime of u and then du dx. Now u is equal to g. So we'll get f prime of g of x dg dx, or f prime of g of x g prime of x. So this is how this rule works. So if you're taking the composition of f with a g on the inside, you'll take the derivative of f first, leaving g alone, and then you'll multiply to that the derivative of g. Squeeze that in there. Multiply by the derivative of g. And we'll do some examples here. So any questions about this? All right. So is it erase all this? So let's take a look. So let's say we have, let's pick a homework problem here. Well, let's say we have this. Let's say we have e to the tangent of x. Now, again, you're going to want to keep along that little sort of cheat sheet of derivatives, these rules that you're coming up with. And again, these are sort of the formulas for calculus that are going to be very, very key. So what we can say is we can say u is the tangent of x. So if we're going to take the derivative with respect to y and x, we need dy du times du dx. Well, in this case, since u is tangent x, this will imply that y is now e to the u. So dy du, that's going to be d du e to the u times, and then u is tangent x, that's d dx tangent of x. Questions about that? So if we let u be tangent x, that turns y into e to the u. And we use our formula for the chain rule. dy dx is dy du times du dx. So dy du is the derivative with respect to u of y. And then du dx is the derivative of respect to u with respect to x of u. And u happens to be tangent x. And so we'll get derivative of e to the u, that's just e to the u. Doesn't change anything. And then the derivative of tangent x, that's secant squared x. And so now what we're going to do, we'll replace this u with the tangent of x. And that's going to be our answer. So any questions about that? So let's do this one. Now, one of the things that are kind of, I'll be honest, the quotient rule, it can get a little tiresome. So let's say we have something like this. We want to find dy dx. So we can rewrite y as 6x plus 2 to the negative 1. That we're totally fine in doing. And so then what we'll do, we'll let u be 6x plus 2, which this is going to mean y is u to the minus 1. So dy dx will be dy du times du dx. Now, dy du, well, d du of u to the minus 1 times, this will be d dx, 6x plus 2, or negative 1 times u to the minus 1 times, and this is going to be, you take the derivative of 6x, you'll get 6. Derivative of a constant is 0, so you'll get 6 plus 0. Or negative u to the negative 2 times 6. Or negative, then we have the negative here, the 6 is going to go on top, and we want to avoid negative exponents, so we'll put the u squared like this. Here, let me write that a little differently. We've got u squared. And then we replace u with the x expression, 6x plus 2. And that's going to be your answer. Now, you could use the quotient rule on this one, but you don't have to if you feel more comfortable, say, with a chain rule. Oh, I'm sorry. Let me finish putting the answer in. Squared. There we go. You could use the quotient rule for this one, where 1 would be f of x, and then 6x plus 2 would be g of x. You would get the same answer. All right, so any questions about that? So let's try this one. Let's see. Let's say we have this. Now, what we can do again is let u be 7 plus x secant x. And this means f of u will become the square root of u. So once again, we want df dx. And that'll be df du times du dx. So we're going to take the derivative of square root u times the derivative of 7 plus x secant x. And one thing that's going to help with this, we can call square root of u to the 1/2. Again, roots being some sort of a rational number up here. So we can break this down a little bit. Du u to the 1/2. And that'll be 1/2 u to the 1/2 minus 1, always subtracting 1 with the derivative, or 1/2 u to the negative 1/2. And that's going to be 1/2 times 1 over u to the 1/2, or 1 over, and we'll multiply. 1 times 1 is 1, 2 times u to the 1/2 is u to the 1/2, or we'll just call it 1 over 2 root u. So that gives us d du of u to the 1/2. Now we need d dx of 7 plus x secant x. So distribute the derivative. Now again, the derivative of a constant is going to be 0, but this we're going to need the product rule. And what we can do, this here could be f, and this here, that can be g. And so if the product rule is f prime, so you have x prime times g of x, or secant x, plus, I'll put this in brackets because we're doing our product rule here, plus f times g prime, which will be the derivative of the secant of x. And again, this is one of those things where, you break out your formula sheet. Now 0 plus this, not going to change anything. X prime is 1, so you get 1 times secant x plus x times, and then the derivative of secant is secant x tangent x. And so that's going to give us secant x plus x secant x, tangent x. So now we got to put all this together. So df dx was df du times du dx. So this is going to be 1 over 2 square root u times secant x plus x secant x tangent x and again we can treat this as a fraction with a denominator of 1. And so what we'll get, secant x plus x secant x tangent x over 2 and then the square root. Now we're going to replace u. That was 7 plus x secant x. And that's going to be our answer. So questions about that? So let me show you another one. Now, sometimes things can get kind of buried in here. Let's say we have y is the cosine of 5 sine t over 3. So in this case, things are pretty buried. So we could say like g of t, like u equal g of t, which is t over 3. And so we'll let v be h of u, which will be 5 sine of u. Then we're going to have y, which will be f of v, which will be the cosine of v. And just to reiterate, which happens to be the cosine of 5 sine of u, which is going to be, of course, our cosine of 5 sine t over 3. So when we do our chain rule, we're going to have basically something like this. dy dt is going to be the f prime of v times v prime of u times u prime of x. Or put another way, this will be f prime h g of x times h prime g of x times g prime of x. So you can get multiple layers here. So any questions before we jump into it? All right. So again, let's take a look at our function here. We're going to let u be t over 3. We're going to let v be 5 sine of u. And so this is going to imply that y will equal f of v. Questions about that? Let me write this a little differently. I think there's a better way of putting it. If we let u be t over 3, this means v is 5 sine of u, which this means y is the cosine of v. So what we can do with this, dy dt, well, again, it was f prime of v times v prime. It's going to be of u. We're going to have u inside of v times u prime of t. Or we'll have dy dv times dv du times du dt. So let's figure out dy dv. dy dv is going to be d dv cosine of v. That's negative sine of v. And then dv du will be, let's see, so this is our v. It's going to be 5 times the cosine of u. And then just running out of space here, du dt going to be just 1/3. So questions about that? Because now we just multiply it together. So this is now going to become negative sine of v times 5 cosine of u times 1/3. Or we'll get negative 5/3 sine of v cosine of u. Our t has disappeared so far. So negative 5/3 sine, and then v, what was v? Well, that was going to be, let's see, 5 sine of u. Then we have the cosine of u, and then u was t/3. And so finally, we get our answer. So any questions like that? I'm going to do another one like this. I'm going to do it a little more efficiently. All right. So let's see here. So let's say we have something like this. Now let's say we're taking the derivative of something like this. So what's going to happen here? Just the fan. There we go. Can everybody still hear?
Yes.
Okay. So what's going to happen? We can call this inner part our v. It's going to be 1 plus the cotangent of, oh, let me back up a little bit. So we want to work from the inside out. So what we can do, we'll let u equal t/2. And so that means y becomes 1 plus cotangent of u to the -2. And then what we'll do is we'll let v be 1 plus cotangent of u. And so this means y now becomes v to the -2. So to calculate our derivative, we'll do dy dt. We're going to use dy dv times dv du times du dt. So any questions about that? So figuring out du dt, that's going to be 1/2. And then dv du, well, here's v right here. So this will be 0. This will be negative cosecant squared of u. And then dy du, that'll be -2 v to the -3 to squeeze it in there. Or -2 over v cubed. So any questions about that? So what this means, if we put this all together, dy dv, we get -2 v cubed times dv du, negative cosecant squared u, times, and then dutt is 1/2. So negative and negative is positive. We're going to get cosecant, or 2 cosecant squared, u over 2 v cubed. And then remembering what u is t over 2. And then v is 1 plus cotangent of u. Now we're cubing this. And then again, remembering that u is t over 2. Squeeze that t over 2 in there. I'll put brackets here to differentiate a little better. And so that, there we go, sorry about that. That is going to be your answer. So questions about that? So that's the idea of the chain rule. We're going to expand on this idea in the next section. And we're going to be looking at what's called implicit differentiation. And the idea of that is you can have relations. Now, a relation is not a function. A relation is where you have a function that does not pass functions are relations. But a lot of times with relations, they don't always pass the vertical line test. So like, I'll give you an example. Something like this. Like you want to find the derivative of a function. It looks something like this. Or a relation is what this would be because it fails the vertical line test. So how do we take the derivative of something like this? And a good example would be like taking the derivative of a circle. So how are we going to do this? Well, let's say we have this, and we're going to use the chain rule to help us out. So let's say we have x squared plus y squared equals 1. So to take the derivative of the circle, we'll take the derivative on both sides. And we'll get this. D dx x squared plus d dx y squared is d dx of 1. And again, a derivative of a constant is 0. Derivative of x squared is 2x. And this is going to be 0. So this leaves us with a big question here. How do we handle the derivative of y squared? Well, what we can do is note y is a function of x. So what we're going to do is apply the chain rule. We're going to do it like this. So y equals some function of x. So y squared is going to be f of x squared. And if we let u equal f of x, then, oh, I'll let you write that down, then I'll start up at the top again. We're going to let u equal f of x. So then we have d dx of y squared will be d dx of f of x squared, which will be d dx of u squared. So what this will give us is we're going to need to do d du of u squared times du dx. So we're going to treat y as a function of x. And so what this will give us is 2u times du dx, or remember, this is going to be 2 times f of x df dx, or 2y dy dx. So if we go back, and I'll do some more examples, I'll do them more efficiently than this. But if we go back to the original equation, if we go back to x squared plus y squared equals 1, and we have our derivatives, what this means, if I'm going too fast, let me know. So this means 2x plus d dx of y squared equals 0. What this will become is 2x plus, and we treat this like the chain rule. We get 2y times dy dx is equal to 0. So how does this help us? Well, we want to find dy dx, so we can solve for it algebraically. So this means we'll take 2x plus 2y dy dx equals 0. And then we'll just subtract 2x from both sides. So we get 2y dy dx is negative 2x. Divide both sides by 2y. This will cancel, the 2's will cancel. So what we're going to get is dy dx is equal to negative x over y. So let me do another one. Let's see here. So any questions about that? The idea here is you get to do derivatives of things that aren't functions. So let me do another version of this more efficiently, because that was I think the notation got a little clunky there. So let's say we have something like this. So what you're looking at is something, all the sets, the set of all points x, y, where this holds to be true, where if you cube x, you cube y, you'll get 18 times x times y. And we're going to try to find dy dx. So again, we're going to do the same thing. Take d dx on both sides. Now, the trick to this is we know that y is a function of x. So we're going to recall that y is a function of x. And this means d dx of y, well, it's just dy dx. It's some derivative. Now, we don't have y defined explicitly, but it's going to be something like, it's going to be some derivative of y with respect to x. And that's okay. I mean, someone came along and gave us a more explanation about what the relationship is with y and x, where x is an input and y is an output. That'd be great, but unfortunately, we don't have that. So we'll do our best. D dx x cubed plus d dx y cubed equals d dx 18xy. So the important thing here, this we can do, 3x squared. Got it. This one we have to use the chain rule, where the outer function is the cube, the inner function is the y. So I'll just make a little note. The cubing function is the outer, and then the inner is the y. So that's what we're doing here, and that's how we're applying the chain rule. I think that may be a more, hopefully more succinct way of saying that. So what's going on over here? Well, over here, we're going to have a quotient rule. And the reason is y is a function of x. So we're going to have 18x prime times, and you could think of it as y of x or just y, plus 18x times the derivative of y. And again, y is some function of x. So the most we can say about this is dy dx. That's the best we can do. So what we end up getting will be 3x squared plus 3y cubed dy dx equals, let's see, 18x prime, that's going to be 18y plus 18x dy dx. So the last thing to do is solve for dy dx. So to do that, we'll solve algebraically. Oh, it's squared. Sorry about that. Not cubed, squared. Just careful in your notes. That's a 3y squared. So what we want to do, let's get the dy dx's on one side by themselves. So say we subtract 18x dy dx from both sides. And so that'll give us 3x squared plus 3y squared minus 18x dy dx equals 18y. And again, we want dy dx by itself, so we need to get rid of this 3x squared. And there we go. So why get the dy dx's on one side? Well, what we're going to do is factor out dy dx. So when we factor out dy dx, we're going to get that. And then what we'll do is we'll divide both sides by 3y squared minus 18x. And so what that's going to give us is dy dx is 18y minus 3x squared over 3y squared minus 18x. I forgot a parenthesis. There we go. So that's going to be our answer. Now, what good does this do us? Well, what we can do with this, we can ask a question. What would be the slope of this function at, say, a certain point? Or we can ask that kind of a question. So let me pick up let me do another example here. So let's see here. Let's say we have this. So we've got another circle. So we want to find the slope of tangent lines that are on this circle. So again, we take the derivative of both sides. And we'll get 2x here. This will be, again, it's a function of x. So 2y times the inner dy dx. We treat y as an inner function. The squaring is going to be the outer function. And that's going to be 0. And we're going to get the same result as before. 2y dy dx is negative 2x. And you divide by 2y, you'll get dy dx is, again, negative x over 2, or x over y. So we saw this before. Now, a question we might be asked is this. Take a point that's on this curve, this x squared plus y squared, and find the slope at that point. So to do that, then let's take it a step further. Let's find the tangent line. Passing through, and a point on this curve is 2, 3. Oh, I'm sorry, no, 3, negative 4. Ooh. And you can verify this. This x squared plus this y squared does give you 25. So something you might want to verify, note. X squared plus y squared is 25. So when you're dealing with these kinds of, again, they're relations, they're more generic than a function. You want to work with points that are actually on the curve. And that can sometimes be kind of tricky to figure out what points are on the curve. And this will be 9 plus 16 is 25. So sure enough, that does work. Now, what we're going to do is this. Well, that's our x comma y. And then dy dx, well, that's negative x over y. So now we apply our formula here. We'll get negative 4 over 3. And negative will be a positive 4/3. So that's the slope of the tangent line on the point 3, -4. So what we've basically done, so this is our circle here. So 3, -4, that's going to put us, say, right about here. And so there's a tangent line coming through here with a slope of 4/3. So the tangent line striking this circle at this point has a slope of 4/3. Now let's find the equation for that tangent line. And to do that, we're going to use the point slope formula. Our good old friend from algebra. So in this case, our m is going to be that slope. Now our y1, we'll choose the y coordinate there, and that's going to be -4. The slope was 4/3. You have x minus 3. So this will be y plus 4. We'll distribute the 4/3. We'll get 4/3 x minus 4/3 times 3. Get y plus 4 equals 4/3 x minus 4. And then we subtract 4 from both sides, and we'll get y is 4/3 x minus 8. And so that's going to be your answer. Now, there's another thing they ask you in this section is to find normal lines. And what normal lines are perpendicular to tangent lines. I have to abbreviate that. So they're perpendicular to tangent lines. So what does this actually look like? Well, we'll take our circle. So we have our tangent line. So we found this at 3, -4. And this is our y equals 4/3 x minus 8. This is our circle, x squared plus y squared is 25. You can put your coordinates in here. So what this means is that a normal will be perpendicular to the tangent line. So it's going to be, ooh, that one's a little bit. something like this. Now these become really important in Calc 3. We'll be dealing with a lot of these, and here I'll put that little 9-degree angle there. It's going to be perpendicular to this line. So how do we come up with the normal? Well, again, it's going to be something that's going to be a big deal in Calc 3. So what can we do here right now? Well, there's a rule for perpendicular lines. So for a perpendicular slope, it's equal to minus 1 over the original slope. And again, this little symbol here means perpendicular. So for our situation, our m is going to be 4/3. So the slope of our perpendicular line is minus 1 over 4/3, or minus 3/4. And the other thing we're going to note is that the perpendicular line well, it also passes through 3, -4. So what this means is we're just going to use our point slope formula again, except this time this will be our slope. And we subtract 4 from both sides. What's that going to give us? So 9/4, 4/4, 4/1, we can call that 16/4. So 9/4 minus 16/4, -7/4. Sorry. And there's your answer. So this would give us the line that's normal, or perpendicular to the tangent line. So any questions about that? So the last thing to mention in this section just in case. The last thing to mention is if we're working with multiple derivatives. So in that case, we're looking for, say, the second order and third order derivatives. So just to recall, let's say we have this. The first order derivative is just taking the first derivative of the cosine of x, which is negative sine of x. And then the second order derivative is going to be the derivative of the first order, or in this case, d dx, negative sine of x. And that'll come out to, because derivative of sine is cosine, and then we have that negative attached here, we get negative cosine of x. So we've got this one, we've got this one. And then finally, we could do a third order. Which will be the derivative of the second order. And so what that's going to give us, the derivative of cosine is negative sine. That gives a negative times a negative will be a positive. So we get a sine of x. So just a quick review on taking multiple derivatives. Get that in there. You can quite see it. But yeah, first order, second order, third order. So let's try to take a look at, say, some second order derivatives. Let's say we have something like this. Let's say we have this. Well, let's say we're going to find the second order derivative. Well, again, what we're going to do, we're going to start out with the first. So we'll take the derivative of both sides, just like we did before. And we'll distribute the derivative. What we'll get is 2y, and again, using our chain rule, dy dx. Derivative of 2x is just 2. Derivative of 1 is going to be 0. And this will be derivative of negative 2y, negative 2 dy dx. Again, the constant will pass through the derivative. So what we'll do is we'll solve for dy dx. And so again, we'll do this algebraically. And let's see, we can get dy dx on one side. So again, negative 2 is negative 2 dy dx minus 2y dy dx. And again, we're going to factor out the dy dx. So let me get that up on top here. Give you a second to write that down. If I'm going too fast, please let me know. So factoring out, we'll get dy dx times -2 minus 2y. And again, we divide both sides by -2 minus 2y, divide by -2 minus 2y. And we'll get -2 over -2 minus 2y is equal to dy dx. So this is giving us the first derivative, which is great. We could factor out a -1 here. Negative and negative become a positive, or we just multiply everything through by -1. We'll get dy dx is 2 over 2 plus 2y. And then you can do the same thing with the 2's. You can factor out a 2 and it'll cancel up here. You'll get dy dx is 1 over 1 plus y. So this is our dy dx. Now we're looking for d2y, d2x. So now what we're going to do, we'll take the derivative again on both sides. Now, a thing that we want to do, I'm going to write it off to the side here, but we don't want to forget what dy dx is. We're going to want to hang on to that. And I've got it written up in the top here. I'll put a little box around it. You'll see it when we bring the board back down. So if we take the derivative on both sides, now we can use our chain rule trick here. Now this will be d2y dx squared, and we'll take d dx of 1 plus y to the -1. So we're going to use our chain rule. So that means we're going to treat this as the inner function. This out here is the outer function. And so what that's going to give us well, this will be -1, 1 plus y to the -1 minus 1 times the derivative of 1 plus y. So it's going to be -1 plus y squared times, ooh, I erased my thing, but I have it down below. You're going to have the 0 plus dy dx. This is a 2. There we go. We'll get d2y dx squared is going to be negative dy dx over 1 plus y squared. And this is the reason we want to keep track of dy dx. Dy dx was 1 over 1 plus y. So we can substitute for dy dx. And what this will simplify to is minus 1 over 1 plus y cubed. Or we can bring our minus to the front here. And that's going to be your answer. So any questions about that? All right, so that's going to be it for today. We've gotten through 3.7. I'm still pretty determined to get through chapter 3. What I'll probably do, I don't want to, hand out sort of a thin lectures. So what I might do sort of post a lecture on the weekend before spring break. I might do that just to make sure we're on schedule. But any questions about this? Any question about using the chain rule? Any question about implicit differentiation? All right. So what I'm going to do, oh, I'm sorry, Daniel?
When can we expect the next?
I'm sorry? Daniel, could you try again?
Can you hear me a little better?
I can.
Can we expect the next exam to be after spring break?
The next exam is going to be chapter 3 and chapter 4. So it's not going to be immediately after spring break.
Thank you.
No problem. It's going to be a little bigger exam, or at least a little more content. Now, what is going to come up, though, is the first quiz. Wednesday. So what I'm going to do, I'll give you kind of a study guide for the quiz. And I'm using the quizzes that help you review, mostly for the final exam. I'll have a couple problems that are, I might have 4 problems. I might do something with 4 problems, a couple problems to review what we went over today, and then a couple review problems from limits. And so what I'll do, I'll send out a little study guide, like, look at this example on this page, look at that example on that page. And if you know how to do the examples, you'll have all the skills necessary to do the quiz. And so that's the idea. And it's just to kind of help review and, review some of the new material, but also kind of start reviewing some of the older material. It's hard. I know our finals week is kind of compact. So to kind of help you start doing that right now, I think that would be helpful. So I'll send that out for everybody, and then we'll do the quiz. What I'm thinking of doing with the quiz is doing it in class. So that means probably at like the end of class, I'll take some time to just go over we'll save like 10 or 15 minutes at the end of class to do the quiz. Or maybe at the beginning of class. I haven't decided yet. But I'll send a message out to everyone very shortly. So there's no surprise in that regard. But other than that, that's it. So if you have any questions, let me know. And other than that, have a wonderful afternoon. You too.